Hello? Okay, I think it worked. Good leave. Wait, can you see my screen? Okay. Okay. So, first of all, can I get a show of hands of who read the CAN pages? Yeah. Quentin.
Yeah. I've read those things so many times.
Okay. Okay. Does anyone want to write a question that they want me to address at some point in the slides, if you get what I mean? Like, is there, because I'm going to cover my content, but if there's anything specific you guys wanted me to go more in depth in from what you read?
Like now, or should we like?
No, just say it now so I can incorporate it.
But 5 is of the same type in a row, and there's the other one that's switched.
Mhm.
How does decoding that work? What does that process look like? And how does the data sent to it?
5 bits in a row, then change.
5 identical bits.
5 identical bits.
It starts with the
I'm
good stuff. Yeah.
yeah.
Bit stuff. Okay. Anything else?
It's not really a question, but I think maybe just because I know it's like there was a lot of information and it was good to read, but if you could just make sure that you give just a summary of most important things to know.
Yeah.
When working with CAN and in relation to CAN with our card. It's as a summary.
Yep. Anything else? No specifics. Okay. We'll start then. Can I even? Let's read on.
Hello.
Hello.
Hi. Can anybody hear me?
I can, but let me see if I can put you on the
Just want to switch it to your speakers for the laptop.
Oh, is it? Can I not put it on?
Yeah, I was trying to do it before. Just didn't.
Okay.
I just forgot to turn the speaker.
Just speak extra loud when you want to interrupt me.
Well, I just
Okay. Is this any good? I could just shove my microphone in my mouth. I don't know if that helps.
I can barely hear you. Sorry, say that again.
Hello.
Oh wait, say it again.
Hello.
Yeah. Okay, that's better.
All right.
Okay. Introduction to CAN. Talk. What is recording? Can you check? Is it the slide there? Yes.
I'm just trying to. Oh, look at them now. Yeah, it's a slide right now.
Okay. So, what is CAN? So CAN is a very, very, very popular communication protocol. It's used a lot in general automotive engineering. So if you go to a mechanic, for example, one thing that they might do is plug in what they call a ODB tool. And it's literally just like a CAN adapter, and they'll have a DBC file from the manufacturer so that fault codes directly show up and they tell you oh, your brake fluid needs to be topped up, whatever. The same is used in the car. So in our actual loom, we have CAN wire, and we overall follow the same practices that the rest of the industry does. So what is a communication protocol in the first place? you can think of it as a way to bridge between different points. So an example of just a computer, you might have a bridge across USB to a printer so that you can send a file and get it on paper. That link between them, the USB protocol, is facilitating the communication of that image that you want to print and how you want it to be printed. And the protocol itself is defining how that message is sent, but also how it's received. So a way you can think of it is sort of like a translation. So different protocols are sort of like different languages. There's expectations, there's set standards for how you do things. And when you agree to use a protocol between two systems, you have to sort of make this agreement between you that you're using the same sorts of message definitions. There's going to be this guy here, I'm going to do this like this like this. Everything has to be mutually like accepted between the two nodes so that they can communicate effectively and not have any transmission errors or like corrupted information that you're interpreting differently from what the first guy sent out. So what does this look like physically? Well, for CAN, you'll see there are two wires. One's typically characterized as high and the other low, and they're impedance matched twisted pair wires. So when we buy the wire, it's literally like specific for CAN, and the wires themselves have this impedance rating that we're working with. I'll cover this a bit more, but that in general is related to this concept of termination for CAN. So twisted pair means we're literally twisting the wires around each other, just like you see in the image. And impedance match is the termination concept that I'm talking about. So in general, two wires is all you need to use CAN. Now, a question that is very, very reasonable is why do you even need CAN? Why do you need a communication protocol in the first place? Could I not just have wires for everything? Like, can I not just have one wire that goes high if there's a fault here, and one wire that goes low if I want the window to go down or whatever in like a car? Well, you can, but the issue is that communication protocols are effectively trying to solve this sort of not exponential complexity, but like very much a growing complexity with having to add so many things. And you'll end up like this is an exaggeration. It will be very messy to the point where you're going to have a lot more work managing these different wires and the overall size of your harness instead of just getting on with your work and having something that's light. So a visual representation might look like this if we went without CAN. So you have like multiple wires going between different nodes. So depending on how many signals you need to transfer, you're going to be increasing that bundle size. But with CAN, you can keep things consistently just two wires between them. And there are like trade-offs to them. And sometimes you are going to go with CAN. Sometimes it makes more sense to go with a physical wire. That could be a safety thing, a rules thing, or general, like, I don't got time for this thing. But in general, it's better to keep things on CAN whenever you can. Okay, let's talk more about the physical layer. So when you are laying out what's called a CAN bus, so CAN bus being effectively long length of CAN wire with stubs coming out of it. What is a stub? A stub is effectively a divergence between the main bus path. So you can see here, you have a stub where a CAN transceiver connects to this long length of CAN wire. You have another stub, and you can see that there's this like indication that length of the stub actually matters. And this is true because as soon as you start having lots of different stubs, those junction points into the main CAN bus line, they cause reflections, which I'm going to cover a bit later. Another thing you'll realize is that there are two termination resistors at each end of the CAN bus. So blanket reason, it's for reflections. CAN is trying to be something that is resilient to lots of different conditions. Mainly, we talk about it in terms of magnetic interference and being resilient to that. And if you aren't properly terminating your CAN line, then you add more noise from the messages you send in the first place. I'm going to cover a bit more the details of that soon, but for now, get that picture in your head. We get a bus, and to prevent ourselves from messing up the integrity of our signals, we have to put termination resistors at each end. So 120 ohms at each end looks like 60 ohms when you probe both the lines. Because if you think about it in terms of parallel resistance, you literally have two resistors in parallel at each end of the CAN bus. So often a check that you do is that you will probe for the resistance of the line. And if you get 60 ohms, it's likely that you have the right termination. But the important thing to know is that this value, right, does not mean it is correct. You can't just put a 60 ohm resistor on one end and say, okay, well, the value of my termination, right, when I measure it with a multimeter is correct, so I must be fine. But where this value comes from is actually from the specification of the CAN wire that we use in the first place. So the specification of CAN means that by default, we're targeting for an impedance of 120 ohms. That has to be present on each end of the line. Yep.
Like, do you mean like literally like it's stopping?
Yes.
Yeah, okay.
I'll cover that in a second, but when we talk about impedance of the wire, we're talking about not like there is 120 ohms like across the entire wire. It's a concept called, I think, instantaneous impedance or something like that. The idea is that when you send current, you need to guess, right? If I'm the electrons going through, I need to guess what the impedance is going to be at the end. And that's inferred from material properties, and I don't actually know the details of how that works. But the idea is that when you send this expectation of 120 ohms, you're going to be sending a proportional amount of energy. If you don't have the appropriate termination at the end, then you're going to see that it oscillates. If you think of it in terms of physics, it's just like the stuff of like damping, right? If you don't have any dampener, then you're just going to keep sloshing that energy back and forth. The appropriate way then to see this, if we did terminate it properly, is that as soon as it reaches the end, it just disappears. The resistor is effectively absorbing the energy because there was an expectation that there would be some absorption at the end. So we're meeting that expectation by putting the resistor there. So on the docs page, you might have seen this diagram. So this is the same idea, but explained through the idea of water, right? When I send through a wave of water, if I just have like an end, if I have a wall, then it's going to slosh back and there's going to be this turbulent return of energy as it bounces back into the rest of the pipe with the water. Same idea with energy inside of a wire and like overall waves. If we don't have a termination at the end, then you're going to find that there's going to be reflections, just like this diagram. And obviously they'll dampen over time as they like dissipate over the resistance of the wire. But if you put a termination at the end, then it sort of cancels it immediately and doesn't give a chance for those oscillations to happen. Why are oscillations bad? Well, you're effectively like adding a bunch of signals on top of each other. So what might, I don't think I have a picture for this, but what might look like a normal square wave initially, like, for example, this, right, is what CAN is supposed to look like. You might see something more like this at the parts where it's supposed to be stable, right? In general, it's just way more noisy. That's the idea. So here are some real examples that Sophia and Quentin have taken. This is what it looks like when you have improper termination. You're supposed to be having these clean square waves, but you can see it's literally oscillating. It's just like in MM2, if you've taken MM2, there is this oscillating energy that has to be dampened somehow, and our dampening is the termination resistor. So this is what it should actually look like once you do it properly. Look at the difference. Versus flat square. Okay. Any questions so far about this section? Nope. Okay. Now let's talk about the protocol itself. So remember what we were talking about when we say protocol is the agreement between two parties. How are we actually going to transfer information? So the general idea of CAN is that they are differential, right? What does differential mean? It means that we don't transfer information by the absolute value of one wire or the cumulative value of one wire. It's about the difference between the two wires. So as you can see, with these spikes, right, even though they're going high, if both wires are going high, then it's still a recessive one. So sorry, I should say a 1 is a recessive state and a 0 is a dominant state. You get a dominant state when they pull apart from each other by a certain amount. So you can see here 1.5 and 3.5. So 3.5 minus 1.5, they pull apart by around 2 volts, right? So this guy's going down by 1, this going up by 1. If you have both lines, so CAN high and CAN low, let's say this orange one is CAN high, this low one on the bottom blue is CAN low. If they both go up by the same amount, it doesn't matter because the overall distance is the same. So that is one of the main concepts of it being like twisted pair and being resilient to noise. If you're twisting them together, right, and they're like really tightly coupled, it means that any electromagnetic interference that goes on the line should realistically affect both lines the exact same. So this is called this is called common mode noise because the noise that's appearing is common between both lines that we're inspecting. So CAN is resilient to common mode noise by design, by the fact that the signals are differential. Okay. There is also a bit more depth to this idea of pulling apart and being together. There is actually a voltage calculation that is being done, and in some situations, the CAN protocol fails in unexpected ways. I won't go into depth into this because it's not that important, but you can read about it on the CAN docs page. You likely have, and I can answer a question about it if you want, but otherwise it's not too important. It's kind of like a fringe case. But just know there is an actual calculation for this, which is defined here. So yeah, we're not gonna go into it, but okay. What does a CAN message as a whole look like? So we talked about like there being some way to differentiate between a one, so a recessive, a recessive versus a zero, a dominant. We've talked about the fact that there's this wire and it's twisted and it's resilient. Okay, how do we actually transfer information? Whenever a node wants to transmit a message, it has to follow this format. So there is an indication with the first transmitted bit. So remember, a bit is effectively just whether it's high or low within a certain time frame. Then you have an ID section. So this ID section can be 11 bits, and that's what we use. There's different definitions of the CAN protocol, but for what we use, it's 11 bits. Then you have this remote transmission control request. I can't remember what this is for, I'm not gonna lie. But it's like, in general, you can think of it as overhead of communication between the nodes. And then you have 0 to 64 bits of data. So this is the meat of what we are actually sending, right? All this crap before is just setting up. Then we have the cyclic redundancy check. So that you can think of this as like cleanup. So we are effectively doing a hashing calculation based off of the data. And if this hashing calculation doesn't match up with the data, then we can effectively say that there must have been something wrong with the CAN transmission and the message wasn't received properly. It's a safety check for integrity of the overall data. And then you have 2 bits for acknowledgement. So this section is effectively a portion that allows the nodes that are receiving to assert whether or not they've received this message. If they don't ever assert, then the transmitter is going to try to send it again until someone acknowledges the fact that it is received. Then there's end of frame. Why is it 7 bits? I don't know. Not important. I probably did know at some point, and you probably should read more, but it's not too important for what we're talking about right now. Any questions on this?
Well, like when I was reading, I was thinking about this, is so it's with the way that that these CAN frames are like with like setting it and stuff. Is it like, so I was reading a bit that says like what you need to change to make it so it's receiving or transmitting?
Oh, I think that's the RTR.
Yeah, I think that's what that was, right?
Oh, okay.
Yeah, but does that mean that any node could like change between being like receiving or transmitting, or is it like?
I think it can, because when I was
Yeah.
looking at my project, and so like I can like configure like the specific like header, which is like the entire like CAN.
That was what I was wondering, like if that's not really like set in stone, like you can change it.
Yeah,
Yeah.
like I think, well, at least with like the predefined stuff and the current CAN code, I can just like say this frame is this node is receiving and like transmit. So I believe you can.
Yeah. Low-key, I forgot this was a feature at all. It's not used at all by us. But the way you can think of it is, yeah, you guys pretty much nailed it. If you have a node that instead of like polling, so like I'm gonna send data this amount of time, you have a node that's effectively waiting for a signal from another node to send it in the first place. I don't really know. Nah, I don't think it does. Like we don't use it as far as I know. Probably could be some situations where it's useful. I imagine what it's for is to have like effectively conditionals that allow messages to be sent, because otherwise you'd be overloading your bus at different points. Like maybe like in an actual car, maybe it's like, oh, you want to have a bunch of diagnostics being transmitted through CAN at the initial, like before the car actually starts. And then once you have to start sending messages to like the engine, blah, 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 then you might stop sending that RTR thing to request for the data. And then the CAN bus technically is a bit less overloaded from the diagnostic messages, and there's more bandwidth for the rest of communication happening on it. That's my guess, but it's not used for the car. So don't worry too much about it. Okay. So important concept to understand as well is ID arbitration. So let's think back first to when we talked about the ones and the zeros of it being dominant or recessive. The reason this exists is so you have graceful overriding of different nodes trying to speak at the same time. So for our example, we're going to think of 4 nodes, right? So there's a tire temp sensor, there's an IMU, this is the AMS, and this is the MoTeC. These are all going to be trying to send at the same time, but there's an order of priority between them. The way this order is defined is that the lowest ID value, so you could think of it as the one with the most recessive, sorry, the most dominant bits, right? Because if you're using a bunch of zeros, then your number will be lower overall. So you're using more dominant bits. The one with the lowest ID will take higher priority, right? So in this case, MoTeC is the highest priority with OX20. And you have the tire temp sensor at the lowest, sorry, did I say lowest or highest priority?
Did MoTeC lowest?
Yeah.
Oh, sorry. Lowest ID, highest priority. So this guy is going to win over all of these. Please, you see this? So lowest ID, highest priority, wins over all of these. This one, highest ID, lowest priority, everything here beats it. Yeah. So how this looks like in a real simulated step-by-step environment is all the nodes are going to try and transmit its ID, right? So we were thinking about before the frame, crap, the ID comes right after the start of frame. So let's say all 4 of these nodes transmitted the first frame fine of starting their frame, and now they've moved on to sending their ID. Okay. Well, all nodes have a 0 for their first bit. So it's chill. Everyone's gonna send this dominant 0 state. Cool. No issues. Everyone is happy up until now. Everyone thinks that they're in control. Next bit. Now, the tire temp sensor, because it has a higher value, has a recessive bit here. So when we look at the overall CAN bus, so the result of all of these nodes trying to compete, even though this guy tried to drive a recessive 1, all of these other guys with higher priority, they had a 0 in their second bit. And so they override this 1, and the overall CAN message at that point comes out as 0. Not overall CAN message, sorry, that bit for the ID section of the frame. So what's going to happen now is that in the next bit, because the tire temp sensor sees that it got overwritten, so it's going to compare, oh, well, I sent out a 1, but it turned out to be a 0. That must mean I got overwritten. Red line indicates a node has lost and stopped transmitting. It effectively just stops trying. It's like, okay, fair enough. I didn't win. I was not highest priority. I'm just going to stop doing crap. And the same happens for all of the other ones. We keep going through. If they agree, they all think they're in control. As soon as they disagree, so the second one has a 1, these guys have 0, then it gets overwritten by the 0, and the next frame, it's lost it, and it's like, okay, I'll stop trying. And then it'll try and transmit afterwards when it's like free, if that makes sense. Yeah, so overall, in the end, the MoTeC wins out because it has more zeros, more dominant bits, and these guys all lose because they have more recessive bits. So, yeah.
So do the ones that lost out, once the MoTeC's message is through, does it wait for that and then it tries again? Or does it?
Yeah, I don't know how quickly it retries, I'm not gonna lie. I think it's a random timeout. I actually don't know.
It does try.
Yeah, I'd assume what happens is that as soon as it loses, it has a notion of how long it's going to take for the frame to be fully completed. And so it's just going to try and go as soon as it predicts that it is done. So that's likely to do with the fact that there's this end of frame section as well. And this is sort of related, I guess, to that question you had about the 5, was it 5 dominant or I can't remember, but
A bit stuffy.
yeah. This will be related to it where instead of doing the bit stuffing, I actually can't really remember how it actually plays out. Because you don't really have to worry about it when you're using it because it's sort of inbuilt to the hardware abstraction layers and all that crap. What do I do think about it? What about the data? Yeah, I don't know. Maybe I'll think about it more and give an update, but it's not too important. But effectively, this end of frame thing is probably doing like 7 consecutive recessive bits to show that it's done. So it's like a out of spec behavior to show transition between a message starting and being done. I think the same is true for the start of frame, where it's like at default, the line is like relaxed at a recessive state of it being close together. And then as soon as you drive it dominant, then that's the first bit that starts the frame. So it's like, I think so, yeah. I think so, but I'm not sure. I can't really remember. These details are good to have as a background, but realistically, I mean, the reason I forgot is likely because I just don't need it, right? But if things do mess up in funky ways, you might end up having to think about it a bit deeper, like this one time. So good to keep in mind, but not too important. Okay. So what were we up to? Yeah, sorry. So to wrap up what we were saying, if this guy got out prioritied, this guy got out prioritied, this guy got out prioritied, and this was the only one that actually successfully sent its message. And we're going to assume that it got an acknowledgement as well for its message. Then these guys are going to try and send their messages at the same time, probably in the next period of time. That makes sense. Yeah. Okay. I have 2 slides. Okay. Another thing to understand is that the way that CAN works is you have almost always, so we did talk about the RTR, like bit of it wanting to request a message, but that is still technically a transmission, right? You're still kind of sending a message asking for something. So in CAN, the traffic on the bus is always transmission, right? There is no like, I'm going to send out bytes because I'm receiving something. That doesn't exist, apart from the acknowledgement, right? But if someone is transmitting on the CAN line, it is a transmission. And that transmission gets broadcasted to every single node that's on the CAN line at the same time. So if we look back at the bus, all these things that are connected are literally just direct shorts, right? Direct shorts of wire to different points of this single continuous line of wire. So it makes sense, right? If I'm driving this CAN transceiver is driving some message on the CAN line, all the other CAN transceivers are going to be seeing it at the same time. And this is the way that these guys can do their ID arbitration, right? Because they can see what's actively being transmitted versus what they're trying to send. And it's the same way how nodes that are receiving the messages that are being transmitted can drive that acknowledgement bit. So it'd be like, this guy is transmitting something, and then this guy receives it. And so partway through the CAN transmission, it takes over at this acknowledgement point and just says, hey, yeah, I received it. It's all good. Keep going. Does that make sense? Or
So if every node if every node receives the same message,
yeah,
will it only like, I guess, take the data of that message if it's like expecting that message?
yes. I have a slide for this. It was the next slide. There's masking. So even though everything is sort of receiving stuff at the same time, you as the node that's potentially receiving these messages can choose what to listen to and what to not. The easiest way to think about it is literally just that. If I have a set of CAN messages that I could be potentially receiving on this CAN line, you are going to define what IDs you are willing to accept. So I might mask out everything except this 103 message. Then that means whenever I'm waiting to see if there's CAN messages on the CAN line, I only ever receive 103. I just ignore it. When I see the ID transmission coming through and it's like 6BO or whatever, then I just ignore it. I just stop listening, pretty much. Does that make sense? Okay.
What's up with the code IDs for the tin?
This is an extended CAN ID. So this is the next slide, actually. So things to be aware of. We don't really use extended CAN IDs much on the car. It's just not necessary. Typically, CAN IDs that are extended are used for very large systems where you need a higher amount of bits to represent different potential messages. I think there's other reasons as well. There's lots of different implementations of the CAN protocol. Technically, what we use is called Open CAN. And on top of that, there's also protocols on protocols that define how you should define your messages. There's a lot of stuff that you can look into, but it's all not really relevant. Like, we can just stick to what we do and treat it as CAN. We don't have to say it's opening. But low-key, a judge might ask you one day and they'll be like, oh, what do you actually use? Just say Open CAN and then explain you do whatever you do. And they'll be like, okay. When it comes to protocols, people only ever follow protocols because it's convenient. So it might be because like some other nodes are using this convention / protocol, and so you use it so everything's organized and looks the same way or works the same way. Another thing to be aware of is within the transmission of bits, right? There are different ways you can configure, especially with like the SCM HAL setup. You can configure at what point you measure the bit state. There are trade-offs on this. Like if you measure quicker, you might get quicker response. Technically, it's better latency, but it might be a bit unstable at the start because voltages in general have to stabilize when they change, right? There's a transient and it just needs, even though you have termination, you're doing everything correctly, it's always going to be a bit jittery, right? So at that start point, you might want to wait a bit. So that's why this is labeled like sync segment. It's just a portion of time you want to wait till it's stable. So what we do is we typically sample at like 87.5, 75. It doesn't really matter, right? If it's not working, then of course it matters, but it typically works if you go like 75 to 87.5. It's towards the end of the bit phase where it's had plenty of time to settle. Do you guys know why I'm saying this, or like have I lost anyone?
I'm just wondering, like, why do we specifically have to choose where to read like the bit? Like, does it actually matter? Like, well, I guess using that diagram, doesn't matter if we read it from like the second bit to like, I guess, bit 6, or
It's
The second,
it's all a single bit.
oh,
That's the,
yeah.
the 8 time constants.
yeah, sorry.
oh,
This crossing thing is bits. So this is 1 bit.
Yeah.
This is 1 bit. This is 1 bit.
oh, so that's just like Quentin said, just like 8 time constant.
Mm.
Yeah.
So does it actually matter? Like, well, I guess as you said, like as long as you're like after that initial like stabilization, is it just like fine to choose whichever time constant after that?
Yeah, pretty much. Like I've done a reasonable amount of reading at some point, and it was kind of all really pedantic.
Oh,
Like there are reasons for things, but they're not that deep most of the time. Like realistically, they're not that deep. I can show you where you might run into this. So if you're setting up CAN for a microcontroller, this thing takes a while to open. Apparently they actually released the Cube MX2. That's supposed to be quicker. But it only works with the newest chips. So when you're setting up your CAN peripheral on the SCM, there's like a bunch of crap here. Like why do I have to choose so many different things if I just want to set like the baud rate, right? Well, that's exactly what we've been talking about. So this time quanta and bit segment 1, bit segment 2, prescaler. That's related to what we're talking about right now. This is what I like landed on after doing research. Actually, no, I didn't do this one. This because this is the AMS. I don't know. It doesn't matter. It works. You might want to think about it when you're first setting up your CAN. Otherwise, just forget about it. And then the other thing to just consider is that there is baud rate in general. So how quickly you're trying to send these frames. There are definitely trade-offs between having higher baud rates. Like you might just think, oh, why don't we just go to the max baud rate, which is like typically like 1 megabit per second. But the trade-off is between throughput and stability. So if you think about like we were talking about the fact that when you transition between like the recessive and dominant, like the square wave thing, there is transients. The quicker you try transition, the more transients there is, the more susceptible to transients the overall CAN protocol becomes. So you're trading off stability versus throughput, pretty much. Yeah.
Like the can manifest.
Yeah.
And it mentioned that there's like the baud rate, they give like, for example, CAN 3.
Yeah.
Is like 250 kilohertz.
Mhm.
Is there like, with the different lines?
Yeah.
Like, what was the decision you guys made to have those different lines? Was it because the different things need different speeds or?
So
Give an example.
there are two answers I can give you. One is a comp answer, one is a real answer. A real answer is that the team, when they were doing the initial setup in like 2015 for the inverter, the original setting that the inverter packages were at was 1 megabit, and they're both 1 megabit, and they have to be separate because they have the same IDs for the messages. So they had two CAN lines for that. And then they just had another CAN line for the sensors because they wanted it separate for reliability. Maybe they didn't even think about that. I don't know what they thought about. I'm not gonna lie. The reason that it's defendable is you can justify it this way. You can say, well, the AMK inverter has to communicate really quickly with the MoTeC so that we have a tight control loop, right? When you're doing tractive control, changes can happen in the type of stability or like the RPM that the wheels are spinning at very quickly. And so you want to maximize your throughput. Because we're maximizing our throughput and we're at 1 megabit per second, the CAN line overall is more susceptible to noise. That means that we should overall try to limit the amount of nodes we're having on it to make it more unstable, right? The more nodes transmitting more things, more acknowledgement bits, whatever, blah, 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 just hella crap going on and there's more room for error. We want to make sure there's not room for error for the inverters because they're a safety critical aspect of the car. It's literally controlling what the motors are spinning at, right? If you have transmission errors, it could be that a bit flips at the most significant bit and you instantly are now going max torque instead of min torque, right? You give some random answer and it's reasonable answers, right? But we haven't actually we don't make those conscious decisions that often.
Yeah.
It's sort of like post justification of why these things are reasonable. And then you have CAN 3. You have it at 250 kilobits because you don't care about maximum throughput, right? You don't need to have this crazy rate at which your sensors are logging at. Maybe the sensors don't even support it. Most of them don't. Most of them are capped at 250 hertz, 500 hertz, 100 hertz, so on. And so you're trading overall throughput for stability. And so you can chuck everything on the CAN 3 line to simplify it as well. So you don't have a bunch of different CAN lines. That's how you justify it. Yeah.
Reading the other, about the.
Yeah.
And, like the network architecture, it mentions that there is maybe like a fourth line. I know there's like a CAN 4 with, like the Brewster charger and charger.
Yeah.
I thought there was only 3 lines. So is there 4 CAN lines?
Yeah, so there are 3 on the car.
Yeah.
And then when we were setting up this new charger, I couldn't get the software to work to change the baud rate of CAN. So I just had to put it on a separate CAN line because as soon as you start trying to mix baud rates, it just doesn't work.
Okay.
Because you're trying to transmit like in 2 different languages almost, right? There's just no correlation in terms of timing between them.
Yeah.
So that is a limitation of just practical ability to merge the CAN lines. Yeah, I call it CAN 4 just because it's a separate line. Yeah.
I would also like to mention that CAN 3, despite being the lowest baud rate, you'd assume would be the most stable. It's also the one that likes to die the most.
Yeah. That's because everything is on there.
Everything is on that. So any little bit of noise will.
Yeah.
Yeah. If you ever see a CAN line like just shitting the bid, it is CAN 3.
Yeah.
The other two don't. Which is what you want.
Okay, so this is pretty much the end of the slideshow. So this is now when we transition to doing some work on DBCs. So I didn't have time to make slides for DBCs, so I'm just going to pull up the docs page. And I'll give you an idea. So, okay. Can you guys give me an idea of what a DBC is? Nathan, what's your definition of what a DBC is? Did you read the document? Can you guess?
The database of all the different things on a canvas.
Why do you think we would have this?
So you have one source of truth for everything, so they all know what IDs are for what.
Yeah, that's fair. What's your definition of a DBC, mate?
I'm lucky gonna say the same thing. Well, it's
That's
like,
fine to say.
yeah, it's like a database with all of the IDs on the can line that we can accept on that are coming to the can line. So that you know what is what and you can differentiate between the different kinds of messages. And keep track of it. So if you need to define something, you don't give it the same ID.
Yeah. Okay.
I thought it was more, there might be a idea of all the parts, but I thought it was more for decoding a message coming through, like what each byte in the sequence means and the data types and stuff.
Well, I was gonna say very similar stuff, like it's just a database where it contains all the messages and all the signals within the messages, and I guess defining all the parameters that tell us, okay, this is the on a bit position that's associated with this signal, or like the values that you input depending on like the physical hardware and whatnot. But yeah, pretty much just what everyone else said.
Honestly, a combination of all of that. The place to so that you can read, write, and just interpret CAN signals and the messages within them in terms of where the information is stored in the data frame itself, along with how to interpret it as in units and scale. As well as like what Nathan said about having a single place of truth, so that we're not trying to reference. Well, we haven't got a different idea of what a CAN frame looks like on the AMS versus the MoTeC versus everywhere else.
Yeah. Okay. Cool. So I think the first thing to know is that CAN DBCs have never been used in the team. I literally started adding it like a couple months ago. Why it hasn't been, I don't know. Like it's insane to me that it hasn't been done. But to be fair, it took me 2 years to realize that I should be doing it. So that's a lesson, right? You need to do things even if people don't tell you to do them if you want to see things happen. So for ages, the only form of documentation we had, or CAN in general, right, apart from that page that was like explaining how CAN worked, is this docs page that has a list of a bunch of messages, right? So let's use the AMS as an example. So I plugged in my CAN adapter, right? And I was reading the messages and I saw 103. I would open up this docs page. I would go here, AMS fault. Okay. Okay, well, what do the bits mean? Maybe I'll check the AMS page. Okay. Where is it? Okay. Oh, yeah, there you go. Okay, this is actually correct now. It used to be wrong. But you would look at it and you'd be like, okay, so byte 0, bit 0 is supposed to be IMD status, okay. And then at some point it was flipped the other way. And so I would read the CAN adapter, I'd be like, there's no way this is true. This is like saying that the IMD is faulted, but on the MoTeC it says it's fine. Like, okay, interesting. So I'd be like, okay, I think this is wrong. So I changed the order of it. And then I was like, okay, I guess this is right now. And then when it comes to the actual AMS code, in here, the messages are sent like this. You open up this array, right? So 8 bytes. And then you're literally doing what's called bit banging or bit stuffing, right? I'm going like, okay, if the AMS internally has shut down, I'm gonna put the least significant bit of byte 0 and define it as 1. Okay, sure. And then I put those things and then I send it off. Okay, it doesn't seem that bad, right? Okay, I'm gonna go on M1 build. And now we're gonna have some issues. Okay, nice.
Terminal.
Windows terminal.
Just change the files off of it.
Yeah. Quick tutorial. Oh crap. Let's see. Settings.
This is Fedora.
Color scheme. Oh no, that's because I'm using WSL. And then you just click on whatever you want. Okay, so this is a recent thing I ran into when I was doing the DBCs. So we have this CAN message that is being sent from the MoTeC. Okay, so the way this guy defines it is that find this handler, and then they do this, and they set unsigned integer. Okay, so this, first of all, this definition doesn't mean like exactly what I expect it to be. I need to read this. So, okay, bit offset 0 to 63. Okay, so I guess that 0 means bit 0? No. 0 means the most significant bit, so bit 7, because it's bit offset instead of bit position. Okay, kind of weird, but fair enough, whatever. Can comms tx open false? Okay, well, it says true for big endian, false for little endian. So this concept of big endian or false, or sorry, big endian or little endian is made so that when you're ordering bytes, it's my pain. When you're ordering bytes, so let's say I have a byte, let's say I have a message that spans 2 bytes, right? I have some values here, and I have some values here. The idea is that if this is like byte 0 and this is byte 1, in which order do I actually read these, right? And you can't actually just set a baseline of, oh, every message is going to be like this for CAN, because everyone sort of uses different architectures. So basically, as soon as people realize, oh, maybe this is kind of complicated, it's already set in stone and everyone's doing their own thing. That's how most things work. It's like it's too late now to change. But big endian is effectively saying the most significant byte comes first. So I would interpret this as the first byte, and then this is the second byte. And then little endian is saying the opposite is true. The least significant byte comes first. So this is the least significant byte. So technically, I'll read it in the opposite way around. In MoTeC, though, this doesn't actually mean that. It doesn't use the same definitions that everyone else uses. It's effectively saying, I'm going to grab all this information in the 64 bits that you defined, and I'm going to treat this as one message, and I'm going to flip this around. That's just not consistent with anything anyone else does, right? So you see the problem. When I first was working on the Dash, this is in my first year on the team, I had to add, well, first of all, look at this code. There's like, you have to shift these bits, mask these bits just for one CAN message, right? It's just such a mess to read. And the thing that I added, for example, was it was this warning, right? So we wanted a screen on the car that said warning instead of error whenever it got hot, but not hot enough to shut off the car, because it always said error. And then we'd be confused. Why is a car running even though it says error? So I added this thing of a screen that said warning instead of error. To do this, I looked at the messages initially and I was like, okay, so there's this like struct, sure, and that's like internal to the dash. And then we're taking whenever it's this ID, so 0603, and I'm grabbing the first bit, and then I'm grabbing the first byte, and then I'm grabbing the first bit of that first byte. Okay, seems legit. So I'm going to go display update 603 because this is where it's defined. And then I'm going to look here and I want to correlate this guy with what I'm reading on MoTeC. So first bit, first byte, PDoc. Okay, cool. So, okay, so if shutdown PDoc as integer equals 1, temp equals 1. What? Okay. Okay, what is temp? Okay. Oh. What the hell? Oh, so they're grabbing all these random variables and then ORing them all together.
Is it temp 1.1, not temp 11.2?
I don't know. So they're grabbing all of these and then they're ORing them together and then what are they doing? Then they're setting this position, create errors. Like, what the hell is going on? And so for a while, I was like sitting here, I'm like, this code shouldn't work. Like, realistically, what I'm reading of the positions. So if one is ORed, then this means that this will have first bit. Okay, that seems reasonable. But then we're putting it at position 56. So if I think about it, if it's the offsets, then I have to start thinking about like, okay, crap. So in MoTeC, they do it based off offsets of the most significant bit. So if they're talking about it being 56, then they're at like the very end, and then like 56 plus 8 is 64, so it's like 1 byte over. It starts here. Like, do you see, like, I made this purposely long because it's stupid, right? You're wasting time trying to figure out these things. With DBCs, it's so much easier. It's so much easier when someone does all the work, right? But I'm doing all the work. So hopefully it will just be easier for you guys in the end. Let's look at it from a DBC perspective. Okay, so I need to add on the dash, I need to add this warning screen. Okay. Well, let's say I didn't implement it into the code yet. We still had to do this bit bashing. Okay, well, maybe it's not that bad. So we need to go 603. Fault flags. Okay, cool. Oh, okay. They've defined all the messages in here. So I needed to define this. Where is the flag? I guess I missed this. How is it to do? Okay, so let's look at the PDoc. Okay, they defined it in bit position 0, length 1, and then they said if it's 0, it's okay, and if it's a fault, it's 1. Okay, seems reasonable. So I'm gonna go in the code, and it's saying bit position 0, and I can look on the side if I want a visual representation. So it's byte 0, bit 0. Okay, so I'll get byte 0, and I'll end bit 0. It's not too hard, right? As soon as we start implementing the DBC into the code as well, then it's even easier, right? We would go something like the vehicle dot errors dot PDoc equals, and we'd have a struct that's defined by this DBC, right? It's just like a, literally by the name, it's a structure of messages. And then we'd go something like can3 dot message dash faults flags dot signal PDoc shutdown. Boom. I literally can't get it wrong because by definition, everything is pre-baked into this DBC. There's no messing around. I can't accidentally type this. It works or it doesn't work. Simple as that. That's the motivation behind using DBCs. Yeah. So,
You might have just like off the dome type URL for the.
I think I can. It's UA FSAE and underscore DB.
Bookmarks are.
Okay, so in here you can see in the commit history, I've already done a reasonable few. So the main big one was MoTeC CAN 3 AMS. But I've also done the TEM and the Orion. And then in the issues, you can see it's a lot to do still. So I am sort of chugging through these in my own time, but I will be done. And as soon as you guys start developing things and using the DBC in general, everything should be defined. So it should be easier for you. Okay, so we've talked about using it in firmware. Can anyone tell me where else we can use DBCs? Yeah. Yep. Do you know how? Yep, all good. But you're right. It is just literally with the CAN adapter.
Yeah.
So I think I have a picture here.
We did this thing.
Yeah, we did. That's okay. So previously, right, before the DBC, you would just have this message defined, and you would either have to dig through the code or through some documentation to see what this means, right? I'd have to look at it and I'd say, okay, so this is byte 0, 80, okay, 80 expands to 100, and then this. Okay, so it's byte 1. So I look at the documentation. Okay, AMS fault latch is, although what it's actually IMD shutdown fault latch. But now you literally just import the DBC and you can just read it. There you go. IMD shutdown latch fault. Cool. It's easy. It's really, really easy. Okay. Any questions so far? We can move on to like a practical demonstration of writing something out. Or anything else that you want to cover that I've lost you guys on?
Shooting stuff.
Yep.
Like what's important to do? Like
To do?
Like you're using the CAN adapter.
Mhm.
Like what is like a good thing to look out for?
Not really too much anymore. Like before it was the main thing is like make sure you're looking at the correct piece of documentation and like you know what's up or you can read the code. Now it's low-key as easy as it can get. If the
Yeah.
person that defined the DBC did their job and it's actually accurate to what's being sent, so long as you define these like interpretations or even like comments that explain
Yeah.
what it's for, you just have to read and like apply some judgment to like think about what these things are saying.
Yeah.
So
Is it like the bit that you like hadn't added yet?
Mhm.
Once you're all done, like what is let's say there's something that's missing or
Mhm.
there's something that's new that's added and you're like troubleshooting and it's like not coming up.
Yeah.
Like what do you do in that situation?
You would look at the DBC.
Yeah.
So if you're suspicious of something being wrong with the DBC, then you'd open up this program, KVassar database editor. So I'll show you from the start. If you open it up, it looks blank. Click open. You go to your folder where you cloned the CanDB repo. Where'd the repo go? Oh, you guys know what repo I'm talking about. And then you open the .dbc file. And when you do, you get presented with this. So I'll give you a little tour, first of all. This sidebar, Loki don't use ever, but it's, I think, only there for you to be able to search for things. So if I was looking for status specifically, I can search for status and then it'll click and open this up. Otherwise, I pretty much just scroll through here most of the time. You'll often have it like sorted by hex value, and you'll go looking through. What are some other things? There's this tab where it's like all the signals, so it's not grouped by messages. So do you guys actually know the distinction between a node ID, a message, and a signal? No? Okay. So a node is anything that has a transceiver, right? So this might be a laptop with a CAN adapter. This might be the MoTeC. This might be the ISO current sensor. This might be the AMS. This might be the Orion TEM. This might be the Orion BMS. And I'll keep adding stuff, right? That's what this list, the list on GitHub was for. If you have a transceiver and you're someone that is potentially receiving or sending something, you are a node, right? And the only reason that nodes are defined within the DBC is first for organization, and second, this communication matrix. This communication matrix, low key, I'm kind of new to it as well, but from what I understand, it is only here for when you use the DBC for generating files. So I'll give you an example. Let's say I am generating this DBC file for the AMS, right? Well, the AMS, it doesn't care about all messages. It's just like the idea of masks, right? I just don't care about what the ISO sensor or maybe the CAN adapter is going to say. So if I define everything between them, so if I say like, okay, well, the AMS is sending these, and then the AMS is receiving these, so I mark it with this, then that means that when I generate the file, I want the definitions for the messages that I could be receiving. It's just to like shorten the file, because I don't want all the messages I don't care about, right? And I imagine, I haven't actually looked for it, but I imagine that when you generate the files, you also get a mask that you can use directly so that you don't have to like, well, it's not trying to receive those things and you're ignoring it. It just doesn't try to receive them at all. Sorry? Yeah.
What is it?
So there is this tool called CAN tools, and there's a docs page, I mean, their own documentation for it. Effectively, it's a Python library. How you use it is you go through their installation, read what they have to say, and then realistically, what you're going to use it for is you're going to go into the CAN DBC repo folder, and you're going to go CAN tools. Oh no, you have to go Python 3. Oh, there you go. -m, which is just like using this library as an executable. CAN tools generate _c_source can3 _db.dbc. So I'm just saying I'm using this CAN tools tool. I want to generate a C source file, and I'm inputting this DBC as the DBC I want to use. And then you can also do node and then choose a node based off the definition that you did in the DBC here. So let's say I want to generate it for the AMS. Okay. For the AMS, then I type exactly what this name is here. So node AMS. And then I press enter and I wait, and then it's saying there's an issue. So there is some form of standard for the DBCs, and honestly, some programs treat it more strictly than others. Sometimes you'll see an error on one program, like the Savvy CAN, where you can like use a CAN adapter, versus this DBC editor, where it might not complain or it will complain. MoTeC also complains for different things, if you're trying to use it there. And a note on MoTeC, I don't know if we're going to use it yet because Daniel DeMel has not responded to my message. but it would be nice to eventually use it. It's just that MoTeC, you have to pay for licenses, and updating is kind of scary because in the past the team has bricked, or not bricked, but like soft locked a MoTeC by not doing the update process properly. So it's likely going to be a bit slower to like be adopted for that. Okay, well, we can do a live fix of this. So error DBC, the signals DTC flags 2 and adaptive SOC are overlapping in messages pack state 2. Okay, DTC flags 2. I know where this is. It is in the Orion BMS 06B2. No, B1? Yeah, okay. So what it's saying here, actually, what branch am I on? Oh, okay. So what it's saying here is that I have two messages that are overlapping. So you can see when I click on them, there's this portion that's red and blue. Do you see that? So that effectively means that I defined this message to either be too long and extend onto the definition of another message, or maybe I defined this message to be too early. So I know what I did, and this was a mistake that I didn't fix on this branch. It was just I defined it 1 byte too early. So fix for this, 32 plus 8, 38. Oh, crap. Wait. That's not how math works. There you go. And now it's a bit fine. Probably save it.
Is that because like since you defined the adaptive SoC as bit position 24 and you made that go for like what 16 bits?
Yeah.
Since you had like your bit position for the flag at 32, then it like overlapped, so it didn't actually know.
Yeah, it doesn't know what does those bits actually mean.
Yeah.
Exactly. So you can't have overlapping definitions. That's something that makes it much more confusing for overall the CAN to be documented and so on. I think it's relatively intuitive why you can't overlap, right? Or yeah. Okay. So I save it. Should be fine now. Okay, there you go. Okay, first of all, it's giving me an overriding message. So this is a very real thing as well. So you know how we said that you can only have one message ID per message? Currently, something very stupid about our CAN setup is that when they were setting up the charger for the first time, there is this message that comes from the MoTeC to the AMS that says close the relays, right? It's the wait, where did the comment go? I think this branch is fricked. I don't think this is a normal branch. But anyways, should be a comment here explaining it. But there is this message, right, that comes from the MoTeC and goes to the AMS that tells it close the relays if everything else is fine. When you charge, you don't have the MoTeC because it's not in the car. It's just the accumulator and the charger. And so there is this other message that is also 100 called TS active flag. This message is the same ID, but it's sent by the Orion BMS, and it's faking being MoTeC. It sends the exact same thing, but it's pretending to be the same message, even though they're defined in different nodes. So realistically, this should be a different ID. That's it. And it's complaining because we have two IDs, sorry, the same ID for two different messages. That's it. Does it work? Technically it works, but it just makes everything way more confusing, right? You want to keep things as clear as possible. I shouldn't have to tell you that this is the case. You should be able to just look at it and understand what's going on, right? Okay. So it's successfully generated can3 db.h and can3 db.c. Okay. Let us now look at this file. I just like base code. I just like it more. Okay. This is big enough. Yeah. So this file is freaking huge. But because we defined it for the AMS, it's actually shorter than it would be if we didn't. So this is 662 lines, and you can see there's CAN3, AMS, AMS, AMS. If I stop at any point, it's going to say AMS because they're all AMS messages. These are messages that are defined to be sending to the AMS. That's why they're in there. In general, it's only stuff related to AMS because I set it, the node as AMS, right? If I didn't do that, let's regenerate it again. Now this file is 7,700 lines, right? Because it's every single message. Every single possible thing you might need is defined within this file. Realistically, right, you might think like, oh, should we then delete parts of the code that we don't actually use because it's going to take up stack memory or whatever the microcontroller? That's not actually true because when you compile stuff, you are discarding crap that you don't use. So the final binary is only going to have parts of this file that are actively used. So you don't have to worry about that. So technically, you could just leave it as the entire thing and use it, which I have done for some things. I think for the... Actually, no, I haven't done that. Yeah, but anyways, you could technically do that and it would be fine. It's just like, if you have to find anything through here, there's like now, what, 6,000 more lines that you have to sift through. And often, if you're using like VS Code and you try to do control click, because it's such a big file, it like either just disables control click like search or just acts weird. That's my personal experience. It might actually work, but yeah. Ideally, try to find a node and generate it for the node. So what we were talking about before of the usage with the dash of going like can3 dot dash false flags pdoc shutdown is true. It's actually what we do. There's struct, right? Defined for messages. So let's look for can3 stats. So this is a struct define for this message, right? Let's trace and look through it. In this struct, wait, actually. In this struct, we have AMS fall latch defined as an unsigned integer. Okay, let's look through. Okay. The first signal, AMS fault latch, unsigned integer. Cool. In here, it's got comments, but it also does implement it in the like packing and usage functions. It knows the offset, it knows the scale, it knows the range at which this actual signal can be at. So you can see it's directly baking in all this information into the actual struct that you're going to use. Does that make sense? Have I lost anyone? Do you guys get why this is useful? Okay. Do you guys want to move on to try define one of these then? Okay. Yo,
I was going to ask, how come in the communication matrix the MoTeC isn't receiving anything?
I just haven't done it.
Yeah.
Like I literally made an issue the other day when I realized this exact thing that I just told you guys. Issues are a good way of tracking stuff you have to do. Define communication matrix. Set this up. Here you go. Yeah, okay. We can go through an example together if you guys would like. Yeah? Sounds good. Okay. We'll do one from scratch. So I haven't even looked at this. This might go a bit slow because of that. Does anyone need to go soon? This might take like half an hour. We'll do like one message. I don't think there's actually too much in this code. So steering wheel is some code that hasn't been touched in 3 years because it literally just works. And so there's not much to do here. But it's something we have to define eventually. So I'm first going to clone this. I don't think I have it cloned. Yeah, you can do it if you want to follow along. That's recommended. Otherwise, I'll just ask you guys, like, what do I put here? What do I do here? Yeah, so I'm cloning the steering wheel repository. And you also need to have a Vassar editor with CAN3DBs. So if you're ever adding stuff to the DBC, also make a new branch. So okay. Things open. I haven't looked at this code in a long time. Okay. Do you guys, I can wait for you to all clone it if you want.
I'd probably following along because I don't.
Yeah, all good. Do you have KVaster installed and set up? Open it up with the CAN3 DBC if you want to follow along. Otherwise, we can read through stuff together. Just give me a thumbs up whenever you guys are ready.
It was the CAN-free one.
Yeah. Do you have a charger? My laptop's like you low. One. I see one.
None in the table.
Anyone got a USB-C charge? What power are you on?
13%.
Okay,
What are you
fair enough.
on?
I'm on like 19, I think. Yeah.
Okay, yeah, so we're just like slowly this trickle, yeah.
Sounds good. Are you ready? Yeah, okay. Everyone ready?
Yeah.
Okay. We're doing this from scratch. So, okay, first of all, we need to find where the frick these CAN messages come from. So I'm gonna look at the docs page first to see if it even comes from the steering wheel. You never know. It'll be something completely different to what you expect. So I'm gonna go here, I'm gonna go search for steering wheel board inputs, and it's saying source is from the steering wheel board to the MoTeC. It's message ID 400. Is there anything else steering wheel? No, there is not. Okay, so I'm looking for this message defined somewhere in this firmware. Something I could do, right? I could look through all the files and look for OX400. Oh crap, how do I use this program? Okay, it's like control, yeah. Okay. Okay. Interesting. I don't see OX400 defined anywhere. Okay. 8-way rotary encoder. Payload, okay. Okay, CAN payload. Maybe I'll search for CAN. Oh, a lot of things have shown up. And add message pointer in the header file. Here we have hcan, tx mailbox, phone box. Okay, so it seems like in the main file is where everything I need is. Okay, so this is the header definition, can mode, normal, so it's not extended. This is the normal config. And payload, can tx header, message ID. Okay, where does this come from? OX222. Huh? Okay, so there's a mismatch. I'm gonna look now at MoTeC because MoTeC is the one that's receiving this. So maybe they named it OX222. No, they didn't. Okay, we need to look for steering wheel then. You might want to just watch for now, because we're jumping all over the place, and then once we start defining stuff, you can follow along. So steering, position, okay, interesting. Well, it's, from what I know, right, the steering board isn't actually doing steering angle. That's a potentiometer. What it's actually doing is like the buttons and the rotary switches. Yep. So I'm gonna look for rotary, for example. Okay, rotary. Okay, so buttons. So first of all, you can see the steering board is actually under dash. Who would have known? Who would have known? Okay, dash, buttons, raw input, rotary. Okay, can. Okay, there's 2 channels. Okay, interesting. Update on enter. Okay. Mode mapping. Okay, it's just like copy pasted if statements.
I like that as button 1 or 2 or 3 or
Yeah.
6.
Okay, awesome. Okay, what I can do is, seeing that this is under can, I'm gonna predict that either I just had my search too deep because I was searching for steering. It was hiding a bunch of other crap. So I had to clear my search to actually see there's a steering input can update. Holy, lots of copy pasted code. Okay. What I care about first, right, is what is this can ID? Okay, that's the first thing I care about, because when we're defining the message in the first place. Oh yeah, something I like to do is often I make a new file and then I'll define the stuff like everything for the steering. And then afterwards, I'll open up can3 and append the steering file onto can3, if that makes sense. So you can like make a new file and go here and then add a file. So if I added can4, for example, it would merge all the definitions into one file. So I'm going to make this new file and I'm going to add a message and probably add a node. So this is steering board. Okay, I might add a comment. PCB inside custom PCB inside of the steering wheel. Maybe I'll add this note. It's not too super obvious. In charge of the rotary switches and buttons, not steering angle. All right, you can add information if you feel like it's not obvious to people. Okay, fair enough. So we have to find this message first of all. So from what I read on docs, it seems like there's only one message sending all the information at once. And when I was looking through M1 build, right, I only see this one steering can update under buttons. There's the steering input update as well, but I think this is just like internal MoTeC code. I don't see any TX header or anything, so this isn't can. So it's safe to say that this is the only thing doing can on the MoTeC of receiving. You can see RX open. So it's receiving this message that comes from the steering board. So I need to find what this can ID is. Where does this come from? Okay, it's a parameter. That's annoying because a parameter is set in real time in tune, right? So it means that I have to open tune now. Yeah.
If it doesn't, it's a quick fix committed 4 years ago.
Okay, so I'm on Tune now, and normally to use Tune, you'd connect it to the MoTeC with Ethernet, and then you would get it, like you would click OK, and then it would download the package and all the config, and then you'd see. But I can't connect to the MoTeC, so now I gotta go to our drive and get a config. But I already have this on my computer, so I'm gonna skip that step. I can open package, sure. File, import configuration. They'll probably all be the same. Okay, ignore the warnings. And I'm going to look for steering. So it's here. Position, resources. Oh yeah, I forgot. It's under the dash. Okay, sorry, dash, buttons. Forgot where it is. Let's look. It's buttons, raw input. Okay. Raw input mode can. Okay. Can. Okay. So docs was wrong. It is OXO2222. Prime example. I even script this, right? Prime example of how terrible the system is. You can literally never trust something. So every time I would get asked to fix something on the car, I'd have to do this whole shenanigans to figure out what was even the definition in the first place. Okay, let's write this DBC. So we have ID, we know it's OX0222, it's just OX222. Cool. And now we can go back to just looking at the actual firmware. Well, I read before, I don't know if you guys remember, it said CAN standard. So I know that it's not an extended ID. I don't know, sure. I think it said normal actually. Yeah, CAN mode normal. So I know it's not an extended ID. So I can leave this frame format as standard. DLC means data length carry, I think is the actual wording for it. It's just how many bytes do I have? So am I using the full 64 bits of the frame? I don't know. Let's look at the code. I'm just gonna close these. I don't know. So, wow. And payload size, DLC, okay. 5. Okay. Sure. Okay. TX node, it's steering board. And what is this message going to be? Well, it's literally holding like everything. It's holding both the button read, rotary read, paddle read. So low key, maybe we'll call it like steering underscore inputs. Right. So I'm just thinking of like a reasonable name. I'm taking a bunch of sensor inputs of the rotary, the paddle, and the button. So it seems reasonable. Anyone have any objections to this name? Anyone can think of a better name? No? Okay.
Convention is just all caps with underscore.
So in the docs page, naming conventions, nodes, all capitals, messages, all capitals, signals, lowercase. And it's snake case for these, and then screaming snake case for this, and yeah. The reason I picked these is because it low-key just looks good when you generate the code. And this is like what you should be having your variables defined in C. This is the standard convention, so just keeping everything sort of the same. Okay, so we might add some comment. Okay, so from what I saw, it's reading the button. Is there only one button? I don't know. How many buttons are there? There's 6 buttons. 6 buttons defined. We actually only use 4. Right? So buttons. Paddles used to be a thing we don't use anymore either. Rotary, switch, input definitions. Actually, what have I called the other ones? So something good to do is like, oh, I've forgotten what I normally name things. I'm just gonna check. I'm gonna go back and look. So I'm gonna open up can 3. Let's see. My comments are, this seems reasonable for the actual name. It's relatively close to what I call other things. See, there's actually kind of a discrepancy in how I'm naming things. Some things I'm calling it AMS underscore status. So like the node name and then this other descriptive name. And sometimes I'm just calling it a descriptive name. Could be good to change it to everything be the same. Yeah. What am I putting for my comments? I'm putting primary accumulator, electrical parameters, battery capacity tracking, and message validation. So I think I'm just going to open up a different tab. I think, I mean, if I just said steering inputs, it would just be saying the name, so it's kind of useless. So I'm just going to put buttons, paddles, and rotary switch readings. Maybe that's not necessarily as well, because technically I'm going to be defining these signals with their own names. So I don't know. You can kind of go either way. Okay, another thing we have to define for the message, gen message cycle time. So on docs, I talk about it, gen message cycle time. So this is an integer that is the exact period of transmission in milliseconds. Why is this useful? Well, when you are doing firmware, you can do something like this. You can go like, if can3 underscore AMS, dot AMS status dot period. So you can check against like the period that it's supposed to be sending to do your timing or whatever. Just, you're once again just providing more information to keep everyone informed of what's going on. So now I got to figure out what it is. Oh, there's actually this message that says can message delay 100. So should I trust it? Low key, no, because we've seen a lot of things that have misguided me. So maybe this macro isn't even used. So let's see where it is used. It's not used. It's only ever defined as a macro. Okay. So now we gotta dig deeper. Where is this sent? Okay, so we're setting payload values here, and then we're doing some crap to the header. Hey. No, I don't think it's here. Okay, where else could it be? Well, one thing that I can look for is any definition of messages. So, I mean, functions. So can add tx message pointer. So where is this used? It's not used. That's great. Okay. Maybe I can look for like how underscore can. Okay. Oh, there you go. Okay. So line 498 of main.c. So C. Okay. So this is a timer period elapsed callback. So this I know based off my experience is an interrupt thing based off of the timer and its period expiring. Okay. Okay. So every time this timer expires, I am checking if it's a specific timer. And then I am passing this payload to this other variable. And then I am getting more information, and then I'm overall passing this. Okay. So how quick is this happening? Well, it's saying that it's using timer 14. So again, I'm going to look for timer 14. Okay. So prescale of 73, period 6. Okay. I already know I'm going to have to look at CubeMX now, because it's going to be such a pain to trace through the generated files to piece together what the actual frequency is. Okay, now we need a way. Oh, I already had a CubeMX open. Load project. See. Okay, timers. I know it's timer 14. Activated, prescaler. All right, what is the main clock? Let's look. Clock configuration. APB1 peripheral clocks 48 megahertz. So now let me put up a calculator. So we have, it's counting the full period, but the clock is divided by 74. So we have 48 megahertz divided by 74. So that's the frequency of the clock. And then we are counting up this amount of times, and then we're overflowing afterwards. It counts first the first one, so it goes 0, 1, and then so I'm this answer times 655, 655, 5, but I have to count for 0 as well, so it's 6. Okay, this doesn't make sense. It should be divided because I'm getting I expect to be getting a slower frequency because I'm counting a bunch of times and then triggering the timer once I finish counting a bunch of times. So 10 hertz, okay, seems reasonable. So I'm just going to round it up to 10 hertz, and the period is 100 milliseconds. Any questions? It's crazy, no? Okay. So now I can put in I just remember something. There's a quirk with how KVassar editor works. You can read attributes, you cannot add attributes. So what I actually have to do here is I have to edit it in text or edit it in a different program. So I'm going to ignore this for now because look, it's such a pain. Now let's move on to the signal definitions. We're low-key just going to do 2 because this is really long. No, like you can see there's a lot of work to define these DBCs. Okay, so I want someone to drive. Okay, you guys are each gonna do 1 signal each, and then we're gonna call it there. Okay, Quentin, you're up first. So from before, we had the add tx here, right? So main, let me remind myself, main 498, oh, it's right here. Okay. So I have two ways of doing this definition, right? I can define it based off of what's being transmitted, or I can define it based off how it's being read. For DBCs, we always want to define how it's transmitted, because that's how it's going to be represented physically on the CAN bus in the end, right? So I don't care if this is wrong, because I want this to be accurate. What is being sent has to be accurate, right? Okay. Let's do the encoder first. What do you want to do?
What do you mean, the rotary encoder or the buttons?
Yep, the rotary encoder.
Probably figure out how. What do you want to name the message first, or figure out more information about it being the size and offset, or
Probably more information. That's what I would do.
and then go down to the 8-way rotary encoder function and look at.
Oh, that's easy to read. Okay. It's not great, not great. What we can do, even though we're using the transmission in the end as a definition, we can look at the receiving end to get hints.
Yeah.
And then verify afterwards. So
Encoder was what, a byte?
yep. So based off of this, it's reading 8 bits. Yeah, Loki, this has been going on for very long.
Yeah.
I'm very hungry too. Okay. Oh, thanks.
Yes, it would almost be easier to read it off of. I guess because the MoTeC already mentions the offsets there, but also you can kind of interpret it from the code. But you
So
kind of-
you're right. I think it's very useful to look at MoTeC and interpret this. So it's saying you've got effectively 2 bytes, rotary 1 and rotary 2. Based off the fact that there are 2 rotary encoders, that probably means they're separate values altogether. They're not getting merged together. And if we read through this code, we can see, yeah, they're like 2 different channels that are getting set. Seems reasonable, right? Okay, you're done. You don't have to do anything more. Okay, so Nathan, we are going to define some names maybe, because we now figured out through build that there are effectively like 3 signals, right? There's this button read signal. There's this rotary 1 read signal, rotary 2 signal. So what are some reasonable names we could call these things in here? Yep, let's look. So pack state 2, I have adaptive underscore total underscore capacity. Seems reasonable. So it's just like a description of it, all in lowercase. So what's something we could call this if we're looking at button, for example? Yeah, button underscore states. Okay, seems reasonable. Devansh.
Yep.
What could we call the signal for the rotary? Rotary 1, rotary 2.
Which I named each signal separately.
Yep.
Rotary 1 state, rotary 2 state, maybe.
Yeah, I think state would probably not be the best choice here because the rotary is going to be like a continuous value. So position is good. I like that.
Better position 1, position 2.
Yeah, I agree. I completely agree. Okay, Troy, paddle. So it's like this thing that you just also press. It's like a continuous value.
Oh, so yeah, I guess you could say the same.
Yeah.
Same end then.
I agree. Paddle underscore position underscore 1.
What was the position? That was like.
No, the paddle is like a potentiometer.
Oh.
Okay, seems reasonable. Check that we haven't missed anything. Okay, one thing I've noticed, right? Even though we said button states, they define kind of each button as a separate thing. So one thing I'm thinking of now is we might actually want to separate this button states into multiple different signals. That's just the consideration we can make, right? Because they're all independent from each other, it, in my opinion, makes a lot more sense. But let's just leave it as this for now, because I don't want to spend too much time. Okay. So let's do rotary position 1 like fully. This will be the one example we do, and then we'll end it for today. So off of this, we need to figure out what the type is. So if it's a signed integer, unsigned integer, float, double, we need to also figure out if it's Motorola or Intel by order. So these words are new to you guys, but Motorola means big Indian and Intel means little Indian. It's just industry terms. Mode signal. So there's a few different things that are technically built into the DBC standard. You can do multiplexing in it. Don't worry about it. It's just signal. We have the bit position. So we can see on the side, it's like represented on the wire, effectively like these are your 64 bits and the positioning is like visually displayed here. So this one is like by default defined as bit position 0. So it's starting at 0 here and it's going for the length of 8. So it's going from 0 to 7. And then we also need to figure out what the factor is for interpreting it. So, and the offset. So what this means is, for example, if we received a value, right, of 5 for some reason, if we have a factor of 1, it means that to interpret the final value, we're going 5 times 1, and then we're adding the offset. I don't know actually what the order is. Maybe you add the offset first. That'll be, I think, in the DBC docs page, or you can just search it up online. But it'll be something like this, right? So to get the final value, you need a times by this amount and then add this amount. And then you also have a minimum and maximum value. So the usage of that is that within firmware, you can then check, oh, what is this value? Oh, if it's greater than this, then there's an issue. If it's less than this, then there's an issue or something like that, right? And then you also have a unit. And this isn't a drop-down menu, you literally just type in text. So rotary position can be a percentage. That seems like a reasonable thing. Or actually the rotary position is like stepped. So it's probably not actually going to be a percentage. But for paddle position, it could make sense to map it to 0 to 100. Yeah. So, okay. Okay. Where is the answer? So rotary encoder is what I said we were going to do. So there's this function here and it defines input of payload and then it puts stuff into that payload. So it's saying that if it's O X O, so if the payload that comes in, where does this payload come from? Oh, I just realized something. You know how CAN payload size was 5? It's actually 8. So I'm gonna edit my DBC. Cool. This gets defined here. Oh, and it's just straight up ADC value. Okay, so it's grabbing straight from the ADC these things that are put into here. Bro, they don't even know what they're doing, but clearly it works, right? So whatever, man. If blah, 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 return 01. So okay, I could dig into this, but what I care about is the big idea, right? So it's saying that position 1 is going to return 0x01. Sure. So it's saying that position 1 will literally return this first bit as being true, wherever it's defined in this message. And if I look here for this payload, right, rotary position 1, which it actually isn't defined here, but when I read it from here, this is before that, so I'm assuming this is 1. This one is in byte 1. So straight off the bat, I can say that this bit position of 8 is actually correct because byte 1. Yeah? Everyone with me?
Yeah.
Okay. And then within here, it said that this byte 1 would be 0x01 if it was in position 1. And then if it would be 0x02 if it was position 2, 0x04 if it's position 3, 0x08 if it's position 8, 0x10 for position 5, blah, 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 blah. Okay, well, the thing is, right, this isn't actually that easy to map because it's effectively doing a value conversion to an absolute state. So I need to think about this. How would you actually define it? Because what I'm reading right now is that whatever bit position it is, like if this is bit 0, 1, 2, 3, 4, 5, then this is just what the rotary state is, right?
Mhm.
So this would be rotary state 1, 2, 3, 4, 5. So I can't just do a straightaway conversion and say like, okay, whatever value this gives is the position of it, because it's saying that when it's position 3, the value is 4, right? And when it's position 4, the value is 8. Do you guys see what the issue is?
Could you not just define the length as the maximum value?
The length as the maximum value. What do you mean by that?
Because you're trying to define it here.
Mm-hmm.
You've done the bit position.
Yep.
And the length.
Mhm.
Like, what is, when you're saying that it's hard to like define it,
Mhm.
do you mean like the whole thing or like,
I mean, as in like the interpretation of this overall value, right? Because
because it changes, is what you're saying.
yeah, I'm saying that the mapping is kind of hard to represent, as in I could say, for example, that the value is the position, but it's not true because when we're at bit 3, am I saying this wrong? Yeah, when I'm at position, wait, hold on. When my switch value is at position 3, I'm putting a 1 in byte 2, which technically means the value is 0x04. So realistically, I should do a log base 2, right? But that's actually kind of hard to show here. In this situation, what I would do is I would say something along the lines of rotary switch position reflects bit position plus 1, e.g. position 3 equals 1 on bit 2, meaning value equals 0x04. Not the most straightforward explanation, but I'm explaining how it's currently implemented. And because low-key, this is just the crap way to do it, I would then just say, I'd add a fix statement. I'd say, fix, this is hard to represent cleanly in a DBC. Change steering board firmware. Just make your life easier for yourself, right? If it's annoying to work with, then change it. It's low-key like just bad, in my opinion.
Do you want to discuss like sort of encoding they're using on the steering wheel to present it? Just so, like as part of the example?
Like this?
But yeah, like that, also just saying, they're using this type of encoding, like how we do on the AMs.
Like one hop encoding. It is not easy to work with. It doesn't matter because if I know that I'm eventually going to want to change this, I'm just giving information for the next person that comes after me, pretty much. I'm defining it, so it is there, right? And you could interpret it from this comment, but I want it to be changed, so I'm not worrying too much. I'm not going to make it perfect. Does that seem reasonable? If it was low-key, like fine. If it was something like whenever it was position 1, they returned 1, or something like that, then I would just write numerical value represents position.
Yeah.
All of this stuff is very like gray area and just taste. You just have to figure out what is straightforward to understand. So factor is 1, offset is 0. I'm not going to define these because I don't really care, and there's no unit.
When you showed on the docs for the DBC this, it converts the message to almost like a table of states, right? For each like this thing that you pull. It's not opening up. Does it? Yeah, that table on the left.
On the left, yeah.
So is that conversion happening through the C header files, or is it in some software built into the?
Yeah, it's a good question. So there's a few softwares that use a CAN adapter.
Sure.
And when you connect this CAN adapter, you're practically connecting a CAN transceiver over USB serial to your computer. What that means is that you can sniff out or like be an observer of the CAN line. And this software does the like bridging between serial and the CAN adapter.
Yeah.
So you do something like connection, open connection, add device, and then your CAN adapter would show up, blah, 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 create connection. And then you would assign a bus to it. And then you would come to like file, DBC file manager. You'd add your DBC and associate it with a bus. So you'd like write 3 here. You click, I think it automatically applies it, and then you close it. And then once you start reading frames, which is exactly what it looks like here. When you start reading frames, it's doing its own conversion, like interpretation in real time. It's not using the C values or anything. It's built into the program.
Okay, so it's the mapping is defined in the DBC files.
Yeah.
So you can't really, because I was thinking, obviously with this problem, if it was defined in the C files, you could just edit those and create a mapping function.
Yeah.
Okay.
Cool. I think we can low-key wrap it up there unless there's something you guys want me to explain before we end. Is there anything that feels unsatisfying? Like something that's like, I don't really get this. No?
Oh wait, so pretty much with the implementation of like the DBC files and whatnot, all that code we just saw about like a lot of code just manually like having to like shift the bits, mask the bits. Since we got the generated code from the DBC files, you skip all those steps pretty much.
Yeah. So long as I've done the job of defining everything, which before I leave the team, I will have, you can always just generate C files. MoTeC for now will stay like this.
Yeah.
That's because of the licensing stuff I was talking about and like the complications of upgrading it. But at some point, you 100% can transition it. And I'll show you what it looks like. It looks very similar to how the firmware looks once you get it working.
Task, I read something about MoTeC having support for DBCs.
Yeah.
Um,
So you can see you can import it in, and you literally just go like define a header, dbc.can3.dash glv status tx open. So you open this header, and then you literally just like choose a signal, right? So glv voltage, and then you use a function based off what type it is. So this is we're using the scaling pre-baked in. So set scaled ecu.battery.voltage.voltage. That's it. And then at the end you just go TX and then with the header.
So do you need like a license to use the DBC?
Yeah, I'm not sure. Because I thought the license covered up to this update because when I tested this was on my laptop with the new build installed, but you need the license to like build the package to upload it onto the MoTeC. And it said that the version wasn't compatible, even though on the website they say like you only need to buy a new license after this point. But clearly that's not true if they're not letting me build it. So I don't really know. Not gonna lie. That's why I added Daniel DeMel, because he's been here since the beginning of time, so he would know more context around it. And he was the guy that one time tried upgrading it and then soft bricked it as well. Yeah. Any other questions?
Do we have a DBC for the autonomous car?
Yes, 100%.
Starting it now, make it a lot easier.
And likely there is some like ROS tooling for DBCs as well. ROS to DBC. Yeah, generate ROS2 node based on DBC files. Easy as that. Whenever you're touching CAN, from now on, think DBC first. So in the future, after like I finish defining everything, what will be the like workflow for touching and adding stuff to CAN? You'll first edit the DBC and then you'll edit the implementation. So you like plan out, what do I want it to look like? How do I want it to be interpreted? Blah, 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 blah. And then you just do the implementation based off generated files on the firmware or MoTeC or ROS.
When you say the workflow is editing the DBC.
Yeah.
That's the one, like, the one that's on GitHub.
Yes.
Do we do the same where we like branch it and then?
Yep. So you go on GitHub. I don't have tab. So you go on GitHub, you would like make a new branch off of main, you call it whatever you're changing. So if you're updating something, you'd call it like update slash BMS. If you're adding something new, you'd say like feature, BMS, whatever. If something was broken and you just didn't know, you could do like fix. It's just like keeping things clean and intelligible. Yeah. Any other questions? Okay. DBC source of truth. One source of truth. Very important. Okay, that's all.
Thank
Should I do,
you.
if I do a DBC for the autonomous car, should I do it on the NDB repo or a different one, second one?
want
You
to
can
separate-
3 and can 4 separate files. You could always do it.
Yeah, you can always just do it in the CanDB because,
Oh, true.
like you said, they are just separate files, so it wouldn't really harm me.
Yeah.
Yeah.
I imagine
Yeah.
All I can think of though is, wouldn't it be better to have a separation of issues, like when you're looking through the issues, like the autonomous car?
Yeah.
Separated
you
from.
can also add flags to the issues. right?
Yeah, you
Yeah,
can.
that's true.
You can add flags.
I imagine
Like here, you can add an autonomous one, or you can just like call your issue like autonomous and then put whatever you want.
I also imagine that you're probably decently well trusted with get anywhere
Yeah,
right.
that's true.
So,
Yeah.
Okay.
Stop recording.
Oh.
Hello.
Bye, Peter.
Hello, I'm still here. Hello.
Hello. Wait. Oh wait.
Oh.
Bro, why does that button look like that? That's actually such rage bait. That's crazy. Okay. I can stop recording, right? Yeah. Okay. No more questions, right? No more.
No
Vitor, do you have any
Nope.
questions?
Nope. I
You
kept
sure?
up
You
pretty
didn't
good.
ask a single question though.
Yeah, no, I kept up. It's all good.
You just understood
okay.
everything.
Yeah, more
Okay.
or less.
Sounds good. Okay. Bye bye.
Take a hot minute to stop recording.